Hello there, students. This is Dr. John, your physics and math professor. We're going to be looking at our second pulley problem today. If you haven't seen the other one, just go back. I was a little slower on that one just to give you a little bit more details into how to do things. I'm going to try to move a little bit quicker this time. In this pulley problem, we have one mass, 8 kilograms, I'll call that M1, sitting on a table without any friction. And we have another mass, I'll call that M2, the pink one, at 6 kilograms hanging off a pulley. And we're going to see what the acceleration and what the tension in this string is. Well, first of all, you have to remember a couple of things about these problems. The tension here and the tension here are the same. The pulley just redirects the tension. That's all it does, especially a frictionless pulley. And the acceleration of this box is going to be the same as the acceleration of this box. It may be a different direction because the pulley redirects the force of the tension. So the acceleration may be this way or this way, this way or this way, but it's still going to have the same value because they're hooked together by the string, so the acceleration can't change values. And we're going to look at these. The way that we're going to do that is we're going to isolate each of the systems individually. I'm going to build little boxes around them, and like this. And then I'm going to redraw each individual mass over here, and we're going to isolate that system. So here I've redrawn M1 without the fancy table. M1 sitting on this blue table here, and I've written in isolation, I've drawn an isolation box around it. Now we want to look at all the forces, the forces acting on M1. And we have a couple of them. One, of course, is this M1G. One is a normal force going up. Now, because there's no friction, these forces are not going to be needed for our problem. So I'll draw them in there, but I'll erase them right away because we're not concerned about them. What we're concerned about is this force here. This is the force caused by tension, the tension in the rope. And we now have only one force acting on this that's pertinent. These forces up and down are going to be balanced. And remember, from Newton's law, the net force, the sum of all forces, the unbalanced forces, which I'll just call F here, is equal to the mass, that mass, which is M1 in this case, and the acceleration of M1. So we're going to be working on that, but first we have to do a couple of principles, very important principles. I forgot to mention this at the start of the video. We want to assume a direction of the acceleration. Well, if you look at this one, you realize this mass is heavier, but it's on a table. It's not going to start spontaneously sliding that way. This mass is hanging off a table, it's lighter, but it's going to have to be the cause of the acceleration. So we're going to have to assume this, that the acceleration is in that direction, which means the acceleration is down for this one, and it's this way for this one. So with that assumption in mind, let's take a look at this box here. What do we have? Well, we have the force, which is the mass times acceleration, or M1 times acceleration. It's one universal acceleration for the entire system. That's going to be equal to the sum of all forces. In this case, it's just equal to T. That's fairly straightforward. There's no force going backwards. There's no force of friction because we had this being a no friction system. So there's our first equation. Looks really easy. I'm just going to draw it right up here so we have it handy for later. T, this is equation 1, is equal to M1 times acceleration. Now let me redraw the pink box over here and just redo the same thing again. There we have it. I've redrawn the pink box. The same thing happens to the pink box here. It has a number of different forces acting on it. We want to try to figure out what those forces are. So first of all, we have this one here, the obvious one. This would be M2G. That's the force of gravity acting on it. The other obvious one is this one. It's the tension going upward. Now, what do we know about the acceleration of the system? It's downward. So the mass 2, remember the mass times the acceleration of any system. In this case, we've isolated this system. That's the second part of the tips I'm giving you. Isolate each individual mass in your system and then get an equation from that. It makes it so much easier. So the mass 2, don't forget to put the numbers in there, just like I put M1 in there, times the acceleration is going to be equal to, now we happen to know it's going in this direction, which gives us the tip. We do this one first, because this is going to be the bigger one. M2G minus tension. This is our second equation. I'm going to write it right there. There, I just rewrote this equation right here, so we have them both handy. When I'm doing these problems, and I would suggest you do the same, get individual equations, label them, write them off to the side. You may need them later. Don't discard them on my board. Sometimes I erase them by accident. I don't have them later. So now we have these two equations, and we're going to try to solve them. We have two unknowns, T and A. Of course, you can sort of see, obviously, what you're going to need to do. You can use A I mean, you can use t, because we have t isolated here equal to this. We could just take this value and replace this t with that value. And then we've gotten rid of all of our t's. So let's write out equation 2 right here. Some of the biggest mistakes we tend to make are copy mistakes. Minus, now we have to replace minus t, m1 acceleration. Now don't forget, this here is this here. So we have to put the minus sign in front. Common mistake that we make is we forget to put that minus sign in there. Once you have it, you of course don't need these fancy brackets. Now what we can do is we can take everything with an acceleration and put it on that side. So I'm going to take this here. I'm going to put this one first because it's m1. m1 times acceleration on this side plus m2 times acceleration, that's this one, is equal to m2g. Now you notice you have, similar to what we had in the first one, you can take an acceleration out of this, a out of this, because they're both times a, so m1 plus m2 times a is equal to m2 times g. Now we can multiply both sides by m1 plus m2, that's an m. This side too, m1 plus m2. There we have it. Here we have the final equation. I'll rewrite it right here. I don't need this, so I can erase this. I don't need that either. So let's write this here. Acceleration is equal to m2g over m1 plus m2. Let's erase this just for clearness of mind. Notice again, just like in the previous problem that I did in part 1, here we have the total mass, m1 plus m2, that's the total mass of the system, or you can call it the total inertia of the system, and this here is the total force net. Because the only force acting on it really is m2g. So the total force divided by the total inertia will give you the acceleration of the system. You could almost look at this problem, create this equation without doing any of this work. If you've done a couple of these problems and you come to exam problems and you're familiar with this outcome that you're going to get, you can probably look at the problem, write this equation down, solve it, and almost be done very, very quickly. But we would like to spend quite a bit of problems walking through it so that you're comfortable with it. Let's put the numbers in here now. M2 is going to be 6, so it's going to be 6 times 9.8, which is g, divided by the sum of the two. So it's going to be 6 plus 8, which is 14. What is this? This is it's going to be about 2 in the bottom, so it's going to be about 4. Always estimate roughly, then punch it into your calculator. So I've done that. Let me punch it in and see what I get for the acceleration. I am getting 4.2 meters per second squared for the acceleration. That's something we've asked to get here. I'm going to write that in right here. 4.2 meters per second squared. That seems like a reasonable answer. It matches what we have here. Now we've done the first part of the question. We often will want to get the tension as well. Fortunately, we have the tension tied right in here to M1 very, very nicely. So we can take one of these two. You could use this other equation too, but that's harder. So we want to take that M1, which is 8 times 4.2, 1632. It's about 35. It's about 35. Let me punch it in and see what I get. I got 33.6. So that would be the tension over here. 33.6 newtons. Now in this case, of course, we don't really have significant figures on this. This would be 1. Normally you'd have this given as 6.0 kilograms or 6.00, and then you would round these off to the appropriate number of significant figures. This might, if this is one significant figure, this answer would be 30. If this, and this would be 4. If this was two significant figures, this would be 4.2, and this would be 34. If this is helpful to you, like and subscribe, and check out my next video, part 3, as we continue on to grow in our understanding of pulleys. I'll see you soon. Bye.